First of all, why are we interested in ionic liquid-based electrolytes? There are a couple of reasons, mostly related to the safety of the overall battery compartment. And the first one is they have better thermal and chemical stability as compared to standard organic solvents. And the second one is that they tend to be flame retardant and they have a negligible vapor pressure. On the other hand, there are negative points as well, of course, and they're mostly related to their high viscosity, which in turn translates to a slow ionic conductivity. So we want to understand how the high degree of ionic correlation in these systems affects the diffusion properties, namely conductivity and transference number, and then leverage this understanding to design electrolytes with better transport properties. In order to answer these questions, we use molecular dynamics simulations because they can provide an atomistic level understanding of ionic transport. I'm sure that most of you are familiar with the concept of transference number, but let me quickly recap what it means. Approximately, the transference number is the fraction of total conductivity that is carried by the cation of interest. The cation of interest, of course, can be sodium, lithium, or any other cation. And the transference number is therefore a key measure for cell performance. Our work on understanding transport properties in ionic liquid-based electrolytes can be divided into three works. The first one is the use of correlated transport theory, where we show the necessity of using a fully correlated transport theory to uncover the correct transport mechanism in the systems. The second one, we show that a negative transference number is actually a more general occurrence as opposed to it was initially thought. And the third work is to leverage the understanding of point 1 and point 2 to try to develop next generation ionic liquid-based battery electrolytes. For the sake of time, in this presentation, I'm going to limit myself to point 2 and point 3 in this slide. The first thing we did was to generate models for a couple of systems that are well known in the literature, and what we measure computationally is a negative transference number. We then found that at the same time, a group in Germany led by Monika Schönhoff applied electrophoretic NMR for the first time to these systems and measured experimentally a negative transference number as well. So we asked ourselves the question, okay, but how general is this trend of a negative transference number in this sort of systems? So what we did was to generate more models, changing the anion part of the ionic liquid while keeping constant the counter-cation of the ionic liquid and the cation of interest, which is lithium in all these systems. And what we found is this heat map, where blue indicates a negative transference number and red indicates a positive transference number. As you can see, the trend is pretty much the same across all the chemistries that we investigated, going from 0 transference number, when there is no lithium in the system, of course, going to a negative regime, and then going back up to a positive. To rationalize the results that we have seen, here we look at the cluster population by leveraging the atomistic nature of our simulations. On the x-axis of this plot, you have the number of lithium in a given cluster, and on the y-axis, number of anions in a given cluster. In each plot, as you can see, there is an oblique line which indicates neutral clusters, clusters where the number of lithiums and anions are the same. As you can see, all clusters lie above this line, indicating that all clusters are negative. Additionally, going from left to right, you go from a negative to positive transference number. I want to draw your attention to the small percentage number at the bottom right of every subplot. That's the fraction of clusters in that specific subplot. As you can see, there is a consistent shift from small and probably more mobile clusters when the transference number is negative to a bigger cluster when the transference number is positive. Additionally, we developed a computational protocol to measure the so-called effective charge of the cation. So effective charge, you can think of it as the average over all the lithium atoms and over time of the amount of charge that any lithium-containing clusters carries. As you can see, the effective charge of lithium is negative and goes slowly to positive for higher concentrations of lithium atoms. On these plots, you can also see a couple of black squares, and those are experimental measurements using electrophoretic NMR again from the Monika Schönhoff group. And as you can see, we find excellent agreement between our results and the experimental results. Now we go to our third work, which is how can we use all the understanding that we developed so far to design better ionic liquid-based electrolytes. Our strategy was to dope the ionic liquid with a so-called chelating agent. A chelating agent, if you're not familiar, is a chemistry, a molecular arrangement that quite selectively can coordinate a specific atom or molecule. In this case, of course, we choose lithium-specific ionophores or chelating agents that you can see here on the right. And the idea is by introducing this in the system that this will compete with the anion from the ionic liquid in coordinating the lithium, therefore breaking their correlation and hopefully increase the transference number and hopefully even bring it to positive. So the first thing we did was to generate a model, of course, and then prove that the chelation effect actually is in place in the systems. And we found that the radial distribution function showed us. We now want to understand what's the implication on the cluster population of the addition of the ionophores. In this slide, N, and also in all subsequent slides, indicates the number of ionophore molecules that are added to the system. So in the left, there are no ionophores. On the right plot, there are ionophores. The cluster population is quite different in two major ways. The first one is the clusters in general are closer to the oblique line, indicating that there are more neutral clusters in the system. The second observation is that there are clusters opposed to the system with no ionophores that are actually lithium only. They are not containing any anions. Therefore, the cluster population was quite severely affected by the addition of ionophores, and the ionophores was capable of structurally decoupling the lithium from the anion. Of course, having a negative cluster is only half of the picture to obtain a negative transverse number, because you need a negative clusters that also moves together in order to carry an effective negative charge. So what we did was to define a measure called persistence, which is the measure of how long in time a given coordination environment persists. And as you can see, going from 0 added chelating agents to 150 added chelating agents, this persistence goes down, indicating that not only the cluster population is more neutral on average, but also the cluster themselves decouple in time more efficiently than without the ionophores. Ultimately, what we're interested in are the transport properties. So in this slide, you see the conductivity and the transverse number for different chemistries and different additions of ionophores. As you can see, the trend is pretty general. The conductivity and the transverse number go up. Additionally, and quite remarkably, you can see that the transverse number can be brought from negative to positive. To summarize, we have these three works. In the first one, we show the importance of using fully correlated transport theory in order to successfully predict transport properties of these highly correlated systems. In the second work, we show that the negative transverse number is not a rare occurrence, but is actually quite general in a lot of chemistries. In the third work, we suggested ways to decouple anions and cations in ionic liquid-based electrolytes in order to obtain a positive transverse number. And with this, I want to acknowledge my co-authors, specifically Jonathan Milo at Bosch and Professor Boris Kozinski at Harvard. These are the DOIs of our works. Thank you for listening, and as I said at the beginning, feel free to reach out with any questions that you might have. Thank you.